Okay, today we're looking at instantaneous rates of change, in particular instantaneous velocity and instantaneous acceleration. Alright, so as we know, if we have a position time graph, to find the velocity, we use the gradient. Now, what happens if we've got one that's not a straight line but rather a curve? So we need to know the gradient here at that point. Now, the gradient there at that point would be the same as the gradient of that line there that's called a tangent. So we can't use the normal method that we're used to, so we need to use something else. And that something else comes from calculus. Now, you do a lot more of this in methods, but for now, I'll give you just a brief rundown on it. Alright, so here's a line, so say at point P here, we want to know what the gradient there is, so the gradient of that orange line. But we've only got one point. Alright, unlike these, so say Q1, we've got the gradient of this line here, Q. If I bring that down there, then I've got this line, keep going, I've got this line, go further, got another line, goes there, and so on. So as you can see, the gradient of the green line, so it's getting closer to the gradient of the orange line at all times. So we need to have a look and see how we can get something to the gradient of that. Right, so that's where this comes into it. So if I want to know the gradient of this particular green line here, I can do that. It's just by rise over run. And in this case, I've got two x values. I've got the one here, x, and then I change x by a bit, and that's x plus h. So h is the change by a bit. To find out what these values are, we just substitute the x1s into the formula. So we have the rise, well, the rise is shown here. So f of x plus h minus f of x. And the run, of course, is this bit in here, which is h. So how do we go from one of these to that one? Well, this point here will move down there when h gets smaller. And so when h goes towards 0, here we are on there, so that's the line we're after, so this h value, as we go further down here, that h, that little bit of x gets smaller and smaller. So what we've actually got is the gradient is the limit, not limit, of h tends to 0 of f of x plus h minus fx all over h. And what that is in calculus a thing called del by dx. Alright, so that's a brief rundown on your calculus thing. Now, it turns out, so for velocity, instantaneous, instead of y and x, we've got position and time, so it's dx dt. For acceleration, instantaneous acceleration, we take that from a velocity time graph, so we've got dv dt. Alright, excuse me. Now, I'm just going to show you a basic rule. The rest we're going to do on our calculators, and you do more of this in methods. So, if y equals a to the n, then dy dx equals a n x to the n minus 1. So you bring your old power down, multiply, and reduce your power by 1. So say if y equals 3x to the 4, dy dx will be 3 times 4 to the x to the power of 3, which is 12x to the 3. Right, anything more complicated than that now we'll do on our calculator. Alright, so let's look at an example. Okay, so here's our example. So a particle travelling in a straight line, position x at any time t. There's the equation. X at time t is t cubed minus t. And so we're looking just between 0 and 3. So x at t is t cubed minus t. We're after the velocity at 1.5 seconds. So this is in instantaneous. It doesn't say in the average velocity, it says find the velocity. So the velocity. So we want v at 1.5 t. Alright, so remember velocity instantaneous is the derivative dx dt. Bring our power down, reduce it by 1. Bring our power down, reduce it by 1. Anything to the 0 is 1. So t equals 1.5. Our velocity is 3 times 1.5 squared minus 1. And when you calculate that on your calculator, you get 5.75 meters per second. Alright. Next example. Okay, so this time we've got a bit more complicated thing. We want the acceleration 1 second. So that means a when t equals 1. And the acceleration is the derivative of the velocity. Alright, so beautiful calculators can do this. Okay, so on your calculator, there is you need to have your keyboard on. Sorry, 2D. Calc. I think it is. Then we'll have an iconic thing that looks like this. Right, looks like that. And so that's the one you enter in. So if you push that button, put the bottom one, you can use T if you want, but I'll use X instead of T. And then over here, use the template fraction template, and because there's a bracket around that, use your fraction template, and then press EXE. And when you do that, you'll find that the acceleration, which is dv dt, will be equal to negative 8 on t plus 1 squared. And then we need to just substitute. So at t equals 1, the acceleration is negative 8 over 1 plus 1 squared equals negative 8 over 2 squared equals negative 8 on 4 equals negative 2 metres per second squared. Alright, that's just about it. Now the next bit we're going to do on our calculators as well, and that's if we want to go the other way. So, alright, here's a dodgy photo that it tells us about. So what we're looking at now, so if we go from displacement to velocity, we differentiate, and that's that dx dt stuff. When we go from velocity to acceleration, we differentiate. Again, that's that dd whatever. If we want to go back the other way, we've got to do the opposite, which is anti-differentiation. Now we're going to get your calculator to do that for you, and your calculator can do that for you. And again, it's on the keyboard in the same area. It should be just about next to the other one. And the icon looks like... Alright, here's another dodgy photo. So there's the symbol. That's what it looks like. So we're using our calculator to do that for us. Alright. Okay, so let's have a look at this last example. Right, so here we go. We're given the equation. We want the exact distance travelled in the first 4 seconds motion. So that's the distance from t equals 0 through to t equals 4. Alright, so the distance... Oh, and I forgot to say what we do for anti-differentiation. So this bit, anti-differentiation, the symbol for that is this. I forgot to say that. So the antiderivative of the velocity, not with respect to x, what I'm talking about, it's with respect to time. So here on this one, it's the antiderivative of t squared plus t with respect to time, and it's from 0 to 4. Now that's what goes in those boxes there, 0 and 4. So from 0, the one that's from goes at the bottom, and the one that's to goes at the top. So you just need to enter that in your calculator. It's basically exactly as that. So in your calculator, you're probably going to do it as 0, 4, x squared plus x dx would be the way that you would want to be entering it. Okay, and of course don't forget to have your calculator set in standard. Why do I say that? Well, I say that because the word exact, so it's after the exact value, and you do that and your calculator's going to tell you that's 88 on 3. And if you want to do that, it ends up being 29 1/3 metres. Alright, so that's it. So really, essentially, it's just a little brief introduction into a little bit of calculus and how it kind of relates to what we're doing here. We'll use a lot more of it next year. So for this year, you may be a little bit confused by it now. Don't worry, you'll do some more in methods. And really, you can just stick to your calculator to do it. Alright, that's set number 4.